As we close out our last section here, our last idea in this section, maybe it's a good time to go out and actually get some real life practical experience in this. And so my challenge to you is go out to the park somewhere and see if there's still a playground around that has a merry-go-round. I'm not sure if there is. I hope that there is somewhere. If there is, take a video of it and show it to us. So what I want you to do is go back and remember what it's like to be on a merry-go-round. Remember what it's like to stand in the middle. Remember what it's like to stand at the edge on the merry-go-round. Well, why it's moving. If it's not moving, what's the point? And I know every one of you, you have your favorite place on the merry-go-round, or did when you were a child. Some of it like to be in the center. Some of you like to be on the edge. And I think you learned over time that it certainly felt like being on the edge of a moving merry-go-round was moving faster. Well, that's what my experience was too. But was it really moving faster? Well, it's where we have to have an idea of what's happening. And how we measure speed when we're talking about circular movement, it falls into two categories. One category it falls into its linear speed, and the other one is that it falls into its angular speed. So what we want to have an idea is that let's understand and unpack those two ideas. So I have this equation here where I have its linear speed. I'm going to use the variable v, and that talks about the distance around the arc length, s, divided by its time, which is our traditional understanding of velocity. So the velocity or its linear speed around a circle is measured by how far around the circle you go per unit time. I'll use omega to represent its angular speed, and this is where it's different. Omega is not the distance around the circle, but it's rather the angle that you move per unit time. And so that way is that when you're on the inside of the merry-go-round and on the outside of the merry-go-round, you're both traveling at the same angle per unit time. So therefore your angular speed is the same, but your linear speed is different. And that's what our experience is in that particular case. So is that helpful? Well, sure. The next time you go down the Columbia River Highway and you're heading to Pendleton or going down to Boise in some particular way, or you're going south and you travel along and all of a sudden you see these big white things coming up out of the ground. First you see tens of them, then hundreds of them, and maybe there's thousands of them. Maybe you've seen them when you've flown into PDX. Yeah, we have a lot of wind turbines around. And we're curious, how fast do those things really move? At the tip of the blade, is it really moving or is it just kind of moving slowly? Well, an example I want to explore here a little bit that helps us to kind of get a sense of what's going on is, let's say that I do have a there you go. You've seen that, right? Yeah, that's exactly. It's a white turbine. Well, let's say that this turbine has blades of 10 feet and that its angular velocity or its angular speed, probably angular, is 4 revolutions per second. So every second it spins around 4 times. So the question we want to ask is, well, how fast is the tip of those blades moving? Linear speed. So we'll look at a relationship that we can build between these two ideas. So I don't have all the tools yet. I need to go back and build one more tool that we're going to find useful. And that tool is looking for a relationship between linear speed and angular speed. And one way to do that is I'm going to pull out our arc length formula that we've had a little while ago. And then, like a lot of mathematicians do, they just pull out a random thing out of nowhere, or it feels like out of nowhere, and they get a solution. Well, in this case, my out of nowhere, I'm going to divide both sides by t. And you're asking, well, why by t? Well, you don't really know until you start to stare at it for a second and goes, you know what? That was an awfully doggone good guess. And it was kind of a guess because I introduced the time variable. And I see now that I have the ratio. I have s over t, which is my linear speed. I have my theta over t, which is my angular speed. And so now I have a relationship that equates linear speed with its angular speed. And this tells us something we've already kind of known. The greater the radius, the higher the linear speed that we feel. So now I have this new relationship that I think is going to be very helpful for us in solving some trigonometric ideas. So let's go back to our problem here. I have everything I need to know. What's its linear speed? Well, its linear speed is a function of its radius, which we know is 10 feet, and its angular speed. Well, our angular speed is given in the idea of 4 revolutions per second. Well, 4 revolutions per second isn't quite helpful because I need to have it in a radian measurement. So let's figure out 4 revolutions per second. I need to convert that on down, and I know that I can go 2 pi, which is the distance all the way around the circle per revolution. See what I did there? That's kind of cool. Multiply that out, and you'll notice that revolutions cancel out, and then I'm left with 8 pi over 1 second. And now I have a measurement that I can use. So I'll go back up to my velocity equals 10 feet times 8 pi per second. Multiplying that on out, looks like I'm going to get roughly 80 pi per second. And that's a completely satisfactory answer as far as how quickly or what's its linear speed. But if you want to crank it out and multiply 80 by 3.14, you're roughly getting about 240 plus feet per second is what the tips of those wing blades are doing. So make sure you're not flying around or being a bird when that thing comes crashing in on you. Anyway, I hope that was helpful. I hope that was enough to kind of help you move through the section. It's not going to hit you right away. It's not going to come all of a sudden. It does require some work. And so I hope you look through the problems that we've assigned, and those will give you a good practice to help kind of build your skill set.